today we have an incredible guest, Yury Malkov, staff machine learning engineer at Twitter and one of the inventors of the HNSW algorithm, which is one of the core drivers of the vector index that facilitates this massive information retrieval with the Weaviate vector search engine. And we also have Etienne Dilocker, co-founder and CTO of Weaviate. So this should be such an incredible conversation between hearing about Yury's perspective as the scientist coming up with these things and building these things out, and also Etienne's experience of integrating these things in Weaviate. And I'm so excited to hear the trading of ideas between these two and get into all sorts of details between these approximate nearest neighbor algorithms and details of building up these vector index data structures. So Etienne, can you tell us about your experience with HNSW, how you came across it, and the key questions that you're dying to ask Yury?
Yeah. I don't actually even remember exactly how I came across it, but I do remember that when I saw it, I was like, wow, this is exactly what we need, because we were in that phase of sort of just doing a proof of concept of Weaviate in general. Like, can we add value in that space? Is there value for some things such as a vector database, which we didn't call that at that time yet, because the term basically hadn't been invented yet. But yeah, we were just playing around with just brute force search just to basically prove the concept. And then we looked into, okay, how can we do this at scale? How can we do it more efficiently? And I came across the HNSW paper, and it's like, wow, this is kind of what we need. And I remember the first thing that I tried out was basically, can we incrementally update this? So because for a database, it's very important that you don't just build your data set once and then you have it and then it's basically read only. And yeah, would this be something that was possible? And to my surprise, it actually was. And not just was it possible, but it seems like the entire design about how you insert data into an HNSW index revolves around the idea that you just basically use it to search it, which is really cool for a database. And then we can get more about this later. We added some more things to add filtering to it and deletes and these kind of things, and that really made it a great base for a database. Yeah, so first of all, Yury, welcome, and thank you very much for making that kind of research open, and so that we can build upon it. And yeah, what I'd like to dive into is basically the first question: how did you get this idea? Where does it come from? Like, what did you do, or was there demand? Because I think if I see correctly, the paper was first released in 2016, and even to this day, we're seeing that new users are coming to Weaviate. There's a certain portion who's actively looking for vector search, but there's also a portion of users who don't even know what that is, who just see the benefits and want to get into this. So thinking back 6 years, this must have been such a novel idea. Was this driven by user demand for faster ANN search, or was this more of a research topic basically that interested you? And how did you get to build this?
Hello. So yeah, it has a much longer history. So there was a predecessor of HNSW, and well, yeah, maybe the release of HNSW actually affected by the surge of interest. So the predecessor for HNSW was, like, we call it NSW or MSW. So it was started developing, I think, in like something like 2005, so way before this time. And yeah, I should mention some people who are also working there. So I work with like Alexander Ponomarenko, so Andrei Logvinov, Vladimir Krylov. And the idea there was that we should build a distributed search system that would scale to petabytes, and it was kind of a mix of a symbolic search system and like a vector, but mostly symbolic. So the idea there was, like, we have objects, so like there's Internet of Things, we have lots of devices there, so they have some properties like in a tree form, and we like make a tree form queries and search there, like using that. And the idea was to use small world networks to do that. And so we had other papers based on that, and like this work was picked up by Leonid Boytsov at some point, and so he implemented it in the NMSLib, which is like one of the libraries that you can use for nearest neighbor search. And when he implemented it, he had also worked with some other people like Nikita Avrelian, and also Alexander. So there was it turned out there is an interest, but because before that there was very little interest. So there was interest from the search community, that is who did algorithms for general metric search, but I didn't see any at least much interest from community that did vector nearest neighbor search. So we were targeting at general metric spaces. So and only at some point we switched to this Euclidean and cosine similarity spaces, just because there was a demand for that. But before that, that was a complicated graph space metrics, and well, essentially HNSW was a solution to scalability issues that we have. So the previous algorithm had a polylogarithmic scalability, so it was log n squared, and we realized what was the reason for that. So we made a fix, and that was HNSW.
Wow, this is so cool hearing how it goes back even further, and noticing this transition from metric space into cosine or dot, which we basically use for vector similarity comparison today. And that is actually something that now that you say it, we are using in Weaviate. We're actually also using HNSW for geo search. So this was because our POC that we built was built on Elasticsearch at the time, just for general search, and that was a feature there. And then when we transitioned, we said, okay, we also need a solution to do just geocoordinates, to basically just find what is related or not related, but sort of what is the shortest distance in a circle around it. And I think at some point we just tried this out. HNSW, we already had it. Could we just plug in a different distance function? And it worked. And I kind of almost forgot about it again, but it's super cool to hear that this was actually the history of it. That this is not just a coincidence, but yeah, this was part of where it originally came from. I've mentioned the fact that we can build up an HNSW index incrementally, and this is something that I just have to ask. Was this a design decision, or was this more of a coincidence? So if you say the history is within search already, that makes a lot of sense. But did you actively try to achieve this, or was this basically a coincidence that we can change it incrementally?
That was a design decision. So basically, so it also went from history. So the previous algorithms that we use were kind of the same. So they were based on incremental insertions. But in terms of library and performance, there is a public library that support HNSW lib. So I didn't support features that would block this feature, so the incremental insertions. So and initially the idea was that we are kind of building a peta scale databases, and there it's impossible not to build it incrementally. And so they were distributed. There was we planned that support increasing the size of the storage dynamically, so we can add nodes to the system. So that was a design decision. So it should be dynamic.
Really cool, and especially that you say that you had databases in mind, because when we chose it, well, we knew that we wanted to build up a database, but of course we didn't know that decision. But we basically picked HNSW among other things because it allowed for that incremental. And as you say, for a database, there's really no other way. So something that to dive a bit deeper into how HNSW works, something that you have in there is this, I think in the code it's just called the heuristic 2, which is basically a way to trim the connections and to keep those to the most valuable. Can you explain to our viewers sort of what it does, and then also how you came up with that? Because I think when I read this the first time and saw what it does, I thought it was pretty genius, and I wanted to know, how does one come up with such a heuristic?
Well, yeah, so there are also predecessors that help us coming up with this. So basically, so there is a general no solution to the search in graphs, in proximity graphs. So you have a Delaunay graph, which is like a dual of Voronoi tessellation. So you like every greedy search in this graph will end up at the exact nearest neighbor. So Voronoi tessellation is basically, so you have a space, you have points, and you divide the space so that like each cell corresponds to the nearest neighbors of the element, which is the center of the cell. So it is pretty basic. And so like if you look on theory, so there are subgraphs of this Delaunay graph, because this graph has a huge problem, like huge performance implications if you try to apply it to vector spaces, because maybe so there is like a theorem, we can prove it, which was done in the work on spatial approximation 3, that if you have a general metric space, so you cannot have access to all the points, you don't know like what else points can be in the space. There is no way that you can reconstruct the exact Delaunay graph from those points, or any subgraph, like I mean, not sorry, like the graph that has Delaunay graph as a subgraph. So that will be like fully connected graph. So you can come up with some examples with new points, because that can be arbitrary. So you will have to connect every point to each other, which obviously does not scale. There are subgraphs, and one of the subgraphs, one is nearest neighbor graph. So the graph in which you connect to the first nearest neighbor. So that is also always a subgraph of Delaunay graph, but also there is a relative neighborhood graph, which is also like a subgraph. So there is a general way to extend this graph. So add few edges, because there is like some ambiguity in how you define. So if you just create a relative neighborhood graph, it would not be searchable like for the points inside this graph. So basically you can think of the like this RNG, like extended graph or heuristic. It builds a graph that's supposed to be searchable for the points inside the graph. So if you like one of the points inside the graph and do greedy search, it should end up in this point, so it will find it. So that is a reasonable heuristic, and like a nice property of it is that in the 1D space it goes to just a list. So it translates to a simple list. And that way, like HNSW was like converting into a skip list, which is a well-known algorithm. So this was known before, actually. So I first saw like similar heuristics in the spatial approximation 3, which also had this theorem, which is a nice paper. But like after I first published the paper on arXiv, I did the search and found that it actually was used even before in 1992 or 1993 by Area and Mount. Though even though I had cited actually this paper in my paper, I haven't noticed that they actually use it. So that I was focused on something else. But so this heuristic is like pretty obvious if you think about it. And I know there are some extensions, but so they are all kind of going around it, around the same solution.
Yeah, I would imagine that it becomes pretty obvious if you have that kind of a background on what already exists, and of course also if you have narrowed down the problem, so to speak. Like if you're looking for a solution to basically keep only the most valuable edges and not keep so many. So yeah, I think what's very obvious to you here, yeah, I think this would have taken me or someone else just looking at it without that kind of research background wouldn't have been so obvious.
Yeah, maybe so like a good example where it like is 1D. So that was also initially. So when we wrote HNSW paper, it didn't have this heuristic. But it was performing also like rather well. It was performing much better than the previous algorithm on some data sets, but like it lost to VP3 on few data sets, and so because those data sets were very low dimensional, and we knew that if you just connect to nearest neighbors on 1D, so you will have like lots of connected components. So you don't have a single giant connected components. It's like easy to visualize. So you would need to have a list there. And so like if you target low dimensional data, so that is kind of like also it's simple to understand why you should use it.
Yeah, cool. So next thing on my list, something that we do with HNSW, and this may also be something that yeah, I don't know if it was ever intended, but it's something that works great, and that I was a bit surprised about that it works so great. So one of the USPs in Weaviate is that you can do a filtered vector search. So basically apply your scalar filter in the same way that you would do it in any kind of traditional search engine, and then just have yeah, the vector search only on those allowed items. The way we do it is basically just as this. We have an inverted index. The inverted index basically gives you an allow list of IDs, and then when we traverse the HNSW graph, basically while we follow every connection, which of course we need to do so that we keep discovering the graph, we only add to the result set those that are on the allow list, basically, and that works really well. And at first we just tried it out and thought it was yeah, it led to the results that we expected. And the first time we actually measured it, I was really surprised that the recall doesn't drop at all. Yes, it varies a bit depending on how more you increase the filter, but overall it kept pretty constant. Like even if we went to the very restrictive filters, then of course it gets slower and slower, because in the end it's basically a greedy search or a brute force search through the entire space. But the quality doesn't drop, and the point where it gets slow only comes very late. So what we do in Weaviate is basically like, if we know that the search will be this restrictive, we actually just skip the index. We just do a brute force search anyway, and then only on those allowed IDs. And then of course it's faster again than yeah, having the index search through everything and discard most of the things. Yeah, can you maybe also give a bit of background of why that is, why the integrity basically of the graph keeps so high, or why this works, or if this is something that you've thought about or used this as well, or yeah.
Oh, so yeah, so it's very nice that you made it work. So well, it was kind of intended, but we never tested it. So the idea was that you can change your distance on the fly. So there might be a difference between like the distance which you build the index and which you use for querying, and that is kind of the same thing. So you're like changing the distance a bit. Well, if there is an overlap between the, like, you can think of the if you have one metric and it has some optimal graph, you have a second metric and it has somewhat different graph. If there is overlap in neighbors, so it should work. So if there is an overlap in neighbors, so you filter out those elements, and like most of the, or at least half of the neighbors are the same, so you should have like a decent performance. But yeah, so that is a complicated thing. So like we discussed it, and we had some previous algorithm, but it never, I don't think it ever worked properly. So when we tried it, we ended up in building like special structures to support the search. So you have like a one index match, so you build the sub index for it. So we tried to build that, and like that was pretty messy. And I thought, well, that probably should be the optimal solution. So when you like, you have like your set of possible parameters, and you partition them, like group them, and build separate index for them. If you know that the user is likely to have like search in this set, you can speed up and build a separate index for that. But that is very messy. Like I'm not a specialist in those kind of optimization, so I never even tried it. But it's nice to see that like you made it work.
Yeah, it's interesting that you mentioned the partitioning, because this is also something that we have. I don't want to say we have it in. Yeah, basically have it planned, because the way that we partition. So right now, if you have in Weaviate in a distributed setting, basically the entire index just gets sharded across all the nodes that you have. So basically that means each subgraph, so to speak, or each graph basically just only contains a specific portion. Right now, this is random. Right now, we use basically a hashing function based on the ID, and we are under the assumption that the ID doesn't sort of follow any kind of pattern. So it's basically the goal as of now is just to get it evenly distributed. That I don't know if you have a memory limit on one of the nodes, that basically, yeah, you can distribute it among many nodes. But something that we can do there is we can do that sharding based on one of those properties that we know that would be filtered for. So for example, something that we see quite often is that people want to use multi-tenancy on Weaviate, and that the tenant would then basically be the partitioning key. And then if we have a filter where we say like tenant is 5, then all we'd have to do in this case is knowing, okay, tenant 5 lies on node 3, and node 3 basically has its own HNSW graph. And then from the perspective of HNSW on that node, it's basically an unfiltered search, because yeah, we've already chosen the right graph, which I think is the same thing, basically, or a very similar thing to what you just mentioned. This is actually a perfect segue to the next point. So I want to go a bit into, right now we've talked about sort of why HNSW is the way it is and how certain things work. And I'm also very interested in where things can go from here. So something that I have on my list is just talking about memory in general. So maybe for our viewers, the way that HNSW is designed, and please correct me if I'm wrong there, is basically that both the graph as well as the vectors are held in memory. So that is just an assumption, basically, that's there, which is for fast lookup, basically, both for fast distance computation as for following the edges efficiently. And this basically means that if you have massive data sets, your memory requirements also grow. That of course depends on the build parameters, but as a very, very rough estimate, what we've seen is basically that if you roughly calculate with 2 times the amount of all your vectors, it always sort of more or less matches. As a very, very rough estimate. Exact, of course, yeah, depends on the number of edges. So if we think about billion scale vector search, that is a lot of memory that we could potentially use. And something that we've seen pop up is basically to try and tackle this at what I would call the application side. So something that's been popular recently is binary passage retrieval in the context of NLP. So basically there, the idea is that the vectors get compressed, so to speak, into binary vectors, where each vector only holds a subportion of the information that the vector dimension did before. In BPR, it's basically just if the vector, if each element of the vector was positive, then it's the 1. If it was negative, then it's a 0. So you really basically lose. So if you go from a float 32 vector to this binary vector, you basically lose 31, 32 parts, or basically, sorry, you basically reduce it to 1/30, 1/32 of the original size, lose that kind of information, but of course also lose the amount of memory that you need to store, and basically also increase the search speed. The downside of something like binary passage retrieval is that the way that it's seen right now, you also need to make your model aware of this. So basically, because you're outputting completely different vectors, typically you would have a loss function that would optimize for both the original, both the cosine or dot product or whatever it is loss, and also this binary loss, which would then typically be a Hamming distance between the 2 vectors. So what I'm thinking is that the main topic here being compression. This kind of compression, it's in this case, of course, a lossful compression, but there might also be other ways to do this. If we do this at the application layer, would there also be a chance to somehow get this or other compression techniques, product quantization or something like this, into HNSW itself, so that basically we say the vectors as they are just sort of, they stay the same, your model is the same, but at the index side, we're trying to compress the vectors somehow. Is this something that you could see compatible with HNSW or anything that maybe you've even thought about already?
Well, Yeah, I thought that that is already implemented in libraries. So one thing, like one solution is supported by FAIS. So you can build HNSW, or I think it also now supports other graph indices, or quantized data. So there is an option for that. So I also had I co-authored a paper in ECCV 2018, which also did quantization and HNSW, but from a different perspective. That HNSW is used for cluster selection in IVF, and as far as I know, that is still state of the art and in billion scale search. So you can use much more clusters because you use a graph index. So there, we used 1 million clusters for 1 billion elements, and then you do product quantization there, and with some tricks that my co-authors introduced to save space, and that works pretty well. So I think this solution is better than the one that is implemented in FAIS, or it was implemented. I'm not sure, maybe they support both, because in graph indices there is a so you have an overhead on the links, and it's hard to compress links. So, and if you cluster the elements, so that saves more space. If you put them into a single giant cluster, it loses a recall for sure, but it's a better way to save space than if you reduce the dimensionality of the element, at least to some point. But yeah, so you can do both, and well, there are comparisons in in the literature, so people try that, I think.
That is really great, and that is cool, because I didn't know about FAIS doing this yeah, in a so if I got you correctly, they're basically doing the quantization on the data and then just using HNSW normally. Is that the approach?
Well, yes. So that was published in 2018, I think, on CVPR. So since there were other papers based on that. I think extension, at least I review papers for CVPR and ICCV, so I see that there are follow-up papers coming on that. So, but I'm not sure which of them were published, but that paper was definitely published, and that is a part of FAIS open source.
Nice. This is definitely something that we have to check out, both the implementation as well as the papers, of course. Yeah, on a potentially similar topic, if we're another way maybe of tackling this problem is to also rely on the disk, and something that we've seen pop up is Microsoft's disk ANN, for example, and there they also have the problem that it couldn't be updated. So I think the newest revision is a fresh disk ANN. In general, do you think HNSW, the way that it is right now, could suit itself to storing parts of it on disk, and how would that look like?
Yeah, sure. So I think there were previous papers, though I'm not sure if they're support incremental additions. I think also by Microsoft that used hybrid hardware. So HNSW on top, and quantization and storing in SSDs in the bottom. So that makes sense, but that is more complicated. So you're adapting more to hardware that you have. So it's just it's engineering. It's hard engineering. So you have some hardware set. You need to optimize to work it properly. So that totally makes sense. So that can be SSD. That can be distributed storage. Yeah, but it's hardware.
Cool. Yeah, but it's good to know that it's in general, because I mean, hard problems, to figure them out, that's what we're here for, and that's what our engineers are here for. But it's always good to know that in general, that's a direction that we can go. Speaking of a hybrid approach, the idea of building something hybrid from a very high level perspective is also something that we've had before. We're just thinking, not so much going into changing the algorithm itself, but if we were to just take, let's say, 2 out-of-the-box algorithms, one that supports incremental building and one that doesn't. So for example, if I'm now taking, let's say, Google Scan or something, which is not incrementally updatable, and HNSW, and if I try to sort of build a hybrid system, where the idea that I have in my head right now, but maybe there's way better ideas, would be that, well, we say everything that's continuously imported, basically, we want to keep in the fresh index, so to speak, in the HNSW index. And after a while, we say, like, okay, let's build a second index. So assuming that the data hasn't changed anymore in that index, could we build it up into something like, yeah, in this case, scan, store that, and reset basically the fresh index. And the idea of why we want to keep the fresh index at all in place is basically that stuff is immediately searchable. So that yeah, on database, you expect your import to be immediately searchable. And then, of course, one of the challenges would be, how do we handle deletes? Like, what if we assume a delete comes in the fresh index, then that would be easy, because there we can still handle it before we sort of compress it to the static index. But yeah, over time would probably be some sort of a compromise of marking something as deleted and rebuilding something similar to like a compaction in a traditional LSM tree database or something like this. Yeah, I was wondering, what do you think of this idea? Is there something in general that you say, yeah, there is a potential in these kind of things if we assume that we can use indices that have fewer memory requirements or something like this? Or would you say this is potentially, especially as you already also mentioned, a hybrid approach, this is maybe the wrong approach to combine these things? Maybe there's a better approach if we want to achieve the same goals.
Well, like, as a person who worked on the indices, I think those can be like joined together. So scan is using like trees as like divide and conquer. So, and it has like fast quantization scheme. So when I first saw scan, I heard that was kind of cheating, because like it does not really decrease the computation, but it's kind of speeds them up. And like there was an benchmark, and some of the data sets there were actually integer. But like you can rewrite your metric function to be integer instead of float, and everyone use float, and like you can have a speed up. And I saw that, oh, they're kind of compressing the data, but yeah, scan actually works sometimes better on flow data as well. So, but yeah, you can combine them. There's also, like, for the deletion point of view, I think deletions are pretty costly in graph indices. So HNSW lib supports deletions. So that was essentially, it was like initially it was supported by flagging the elements, which was contributed. And then there was a contribution by adding full deletions. So like when the graph was rerouted, but that is very expensive. So one deletion is like equivalent to like many tens of insertions. So well, essentially it's not deletion, it's an update. But if you flag an element as deleted and then update it to a new element, that is like pretty much the same as deletion. So a reasonable strategy would be, yes, to just flag the deleted elements, and then when you delete like half of them, you rebuild the index. So your complexity does not change. So you have like a constant, because like you delete twice the elements and you rebuild index once. So like your scaling does not change. So I think that will be better. Like from the library point of view, that's up to user. So we cannot just rebuild the index. Like in background, they should be controlled. But like for a library, like for a service, I think that makes sense. So
yeah, this is very interesting that you mentioned this, because this is exactly what we're doing right now. Just we're not. I think we have a relatively short period that we use to rebuilding, basically. So we are doing the flagging as well, and basically then we just have an async process where the user can control when it runs. But basically we do this based on time at the moment, so we don't do it based on the size. So probably, as you say, since it's basically a rebuild, it might be more efficient to basically wait longer, or to maybe make the threshold not so much time-based, but yeah, size-based. We say, I don't know, if 25% or so of the index are deleted, we do an entire rebuild. So that's
like from a point of writing a paper, so you have like some degradation of performance, like in terms of so what would happen if you delete the element? So your performance will go up, or if you add a new element instead, so it will go down because of the new elements. So there is if you set a threshold on performance, it probably would depend on how much, what percentage of the data set you have deleted. So it, like, for a comparison point of view, so that would be like, I think, the optimal strategy.
Yeah, that makes a lot of sense, and definitely something that I think we don't have a lot of metrics yet on what the actual cost is over time, because typically what we've seen in the use cases so far is the deletions are somewhat rarer than imports. But yeah, there's a lot of room probably for improving this. Yeah, coming to my last question actually already. We've talked a bit about the future of HNSW right now, and you've also mentioned that there's of course future research. But maybe as a whole, would you say HNSW is, in a sense, basically it's complete, or would you say there are certain things that should still follow, or sort of, let's say 5 years from now, 10 years from now, do you think the learnings from HNSW would make it into something completely new, or do you think maybe there's things that would be incorporated in it, or maybe something completely different? Basically, how do you see the long-term future of HNSW as a concept, basically? Sorry, you're saying.
I hope that it will last for long. So like the main idea of HNSW is that you can do, like, the main idea that I like, that you can do a search with logarithmic complexity, well, at least at low-dimensional data, with the graph structure. So graph structure is known like to perform well, and you can like have both best of both worlds. So you can have like searching in graph and also logarithmic scalability of the trees. And like graph are probably better than trees because they don't need to backtrack. So if you're using the search index, like, well, not N-node, but like similar with backtracking, so you lose some performance because there is like asymmetry of the links in the graph. HNSW is a simple fix to get the logarithmic scalability. Well, there are many ways how the initial papers can be improved. So as mentioned, the heuristic might be updated in some papers. There is also, I think in some companies and some people use a different construction strategy. So they add elements from the bottom. Like when you have a new element, they add to the bottom layer, and then like only to the higher level that ends in better performance. Also, like there are works on like early terminating strategy. There works on like automatic tuning, so you don't need to figure out the parameters. So right now it's like a big issue for like many of the libraries, that users don't know how to tune the parameters. And like there are, I think, only a few libraries that support automated parameter tuning. And yeah, that is a nice thing. So also there are, I think there is a good direction on improving the graph with ML. So right now it doesn't have any machine learning. So it's assumed that every element in the graph can be like a query, but there might be a query distribution which is like very different. And so it is so there is an application like in recommender systems, like if you don't use inner product distance, but like embed your items in some complex spaces, there is a chance that some items are like they will never appear in search. With inner product, you can kind of tell it because it's like it's usually close to zero. But if you are using something more complicated, or you just like co-embedded in L2, you cannot tell that. But if you have a query set, you can actually understand that some of them elements, they are never returned, and you can just remove them from the graph and don't waste memory and like links on those elements. So yeah, there are many ways to do that. And one of the like future, I thought that it was going to be distributed at some point. So like when you're trying to do like trillion elements in the data set, so like you have to distribute it, and it's not really clear how, like what is the best practical way of doing that. So initially I thought that it's going to be like you have an element and it resides on some node and you have links, so it's mentioned in the paper, so you can try to make it distributed, because skip list was made distributed before, and this is kind of like a skip list in some sense. But that might not be the best strategy. So you still need like a lot of hops, and each hop is a hop to a different node in the network. So that is very costly. You might also want to like aggregate those at some point.
Yeah, so everyone, so I think we've just gotten quite a masterclass on these vector index algorithms. And unless Etienne has one more question, I was going to try to kind of maybe parse this a little bit and give people, maybe beginner people, kind of a little bit, because they might have gotten a little bit lost in some of the details of this. But any more questions, Etienne? Or
no, thanks. I've learned a lot today, and it was super interesting. And I'm definitely very interested in a couple of links to some of the papers that you've mentioned. If you could provide those, that would be super great.
Yeah, sure.
Yeah, I've got quite the reading list too, with I think billion scale similarity search with GPUs. Yury mentioned revisiting the inverted indices for billion scale approximate nearest neighbor search is a recent one, building up on these ideas that we just learned about. But to kind of step back a little bit, I think yeah, that was definitely a masterclass, and you two know so much about these things that I think you do like drill into this language, and just to kind of maybe provide a little more of like a introduction to people. I really liked in the beginning, Etienne mentioned the searching through geocoordinates, and this was the first blog post I ever published on Towards Data Science. Actually, the first thing I ever even put out there before a YouTube video is this idea of doing a geospatial search and using, say, k-means clustering to have centroids that speed up compared to, say, doing a brute force distance calculation between your query latitude, longitude, and then every latitude, longitude in America. So you do these, or wherever you're searching. So you do these k-means centroids. And I think that's a great example for people out there listening to build up an intuition of what we're talking about. Is you structure these centroids and then you can propagate them up. And as we talk about these different ways of, say, having a small world graph, you have this property that small world graphs describes this idea that I'm, say, 6 people away from knowing Barack Obama through my relationships. And that's this network science thing that also behaves nicely with these nearest neighbor distances and this idea of vector distances. One topic that was talked about that I think is extremely interesting is this generalization from, you know, one-dimensional distance. We can use just a binary search tree. Then two-dimensional distance, we get into that geocoordinate search, and then, you know, n-dimensionals, we're talking about these different ideas, like, say, binary passage retrieval that Etienne mentioned, where we have the binary encoding to speed up having to put these massive vectors into the memory. And then things like, one of the things I wanted to talk about and ask about was the locality sensitive hashing algorithm, where say you have a, you know, 10,000 dimensional vector and you just kind of hit, like, I think it's like 50, a slice of, say, 50 of the dimensions to do that kind of distance calculation. What do you think about locality sensitive hashing as a way of computing the distance?
Well, locality sensitive hashing is not learnable. So it doesn't have any learnable component. So that's why I thought it was not practical. So there are lots of like papers on theory. So because you don't have any like dependence on data in terms of the projections. So like you can build some theory and like have nice theoretical papers about it. But like I never saw it like it to be like really practical and to outperform like optimized rivals. So, and I thought that like people who do it, they also see like quantization based algorithms like as better because they are learnable. Like they can adapt to the data set that you have.
So could we also take a little, give a little more background about product quantization? Is product quantization basically the idea of you have your pre-trained embeddings and then you learn a linear mapping into a lower dimensional space from that pre-trained embedding? Or could you give me just more understanding of how product quantization works?
Well, I'm not a big specialist in product quantization, but essentially what it does in its simplest form. So you have a vector, and you want to do quantization, and well, you can do like just quantization of each dimension, but you will lose some information. And what people do, they or on the other end, you can do quantization in terms of k-means. So you have your data, you build k-means, and now you quantize it. But there is something in between, and that is product quantization. So you have your vector, you subdivide it by parts, and you do k-means in each of the parts. And now you have like a subvector, and it is addressed by a k-means cluster in it. So, and that works well, pretty reasonable in many cases.
Yeah, I want to ask one more definition. What are Voronoi regions?
Voronoi regions are so like you divide your space into cells which are closer to some point of your database. Like so, like you have a vector space, you have points, and so you divide just the space around those points so that like every point in the cell has this element as the closest. So basically you divide the space, but by what are the nearest neighbors of those elements.
So as I was listening to the explanation of adding symbolic filters into HNSW, which to me is one of the most unique features that has been implemented in Weaviate, and I think it's such an interesting part of this. Could you tell me more about how this works? I think I'm sorry, I got a little lost in the details of when you were explaining it originally.
Well, you should ask Etienne how it's done.
Yeah, so basically it's really simple from what we do, because essentially we still traverse the entire graph. So if you think of the entire graph as being your full data set, essentially what we do is just, if you come across, let's say there are no restrictions, then you come across your basically your exit conditions at some point, this is my result set. All we do is basically saying, well, if you have something that's on your result set that's not in our allow list, we simply skip it. And then that of course means you need to find something else. So basically you keep traversing that graph space. And one of the reasons why HNSW is efficient in the first place is basically because you don't have to traverse the entire graph. So by basically filtering something, you're saying like, yes, I'm removing, or not I'm removing, I mean, you still have to traverse them, but I'm basically ignoring, I think is the better term, some of those elements. And yeah, the payoff basically is that I need to traverse a couple of more edges and find other result sets. But in the end, basically, you can still find them. I think this is the part that yeah, maybe I can't explain so much, but that we just tried out and that we were surprised by, that the recall is still there. That basically this yeah, integrity isn't lost. The way that we use the inverted index, basically, it's just a tool in front. Like once we start traversing the HNSW index, basically we just need to know which elements do we accept and which we don't, and we happen to use an inverted index. But basically, this like the HNSW graph at that point, it doesn't know where the data came from. Basically, it's just a list of IDs that we allow versus lists that we skip.
Awesome. So there's so much information behind this, and I think it's extremely interesting. And I wanted to kind of transition into this topic. Yury, I saw your paper titled CNN with large memory layers. And I was thinking about memory augmented agents and this idea that you can use these vector structures to have a really massive memory. And I was first introduced to locality sensitive hashing in the paper, The Reformer. That was one of the first papers presenting an efficient transformer model that could have a longer input window than 512 tokens. So I was wondering if you had any thoughts on how we can use these kinds of ideas from vector indexing into, say, going beyond 512 tokens. And I was also thinking that kind of generally, even if you have a slow inference time with, say, a memory that a model that's producing something like abstractive summarization over scientific literature, that that kind of trade-off of slow inference, but for the artifact of an abstractive summarization of, say, papers about vector indexes would be kind of worth it. So I was thinking about if you had any ideas on how you could maybe put HNSW into, say, efficient transformers and that kind of idea.
So you can use NN indices, and so there were works. I think there was like lately DeepMind retro, and before that there were other papers on like supplementing the neural networks with databases. So I think that is a very promising direction, and well, that is very similar to graph learning itself. So you add some context, and well, you can think of that an index can provide like what does it provide? It provides a nearest neighbor graph. So, and like if you treat like you have a document, you find nearest neighbors, and you put some information in the transformer there. You can say that is the typical graph learning. It's just you have an additional input, like from KNN graph. And like those approaches, like HNSW, they are also built on graphs. So you can just use this graph as input, and hopefully, like what I would hope to see is that the transformers would learn to route on this graph. So, and they would be able to do a nearest neighbor search, like what they actually need. Because when you just add nearest neighbors, like in retro and other, there is no guarantee that those neighbors are actually the best information that you can supply for the network, like for the neural network. There might be some elements around, and if you allow the network to route, like select like on which point of the graph you should go, it might perform better. Well, it should perform better. Like might be that like nearest neighbors are not very meaningful.
Because we can, because we can treat the query key value projections and attention as kind of like a vector search also, right? And we could kind of blow up the size of the intermediate query key value matrices and then use these vector searches to, I think it would slow it down a lot, but then you could have, you know, a lot of information, like a mixture of experts.
Okay. So yeah, I think I now I understood the question. So yeah, you can like do something like reformer. So reformers use LSH. Well, you can use also other indices. So here LSH is good because it is fast. So you don't need to build an index for that. But like maybe, well, well, you would probably want to build an index here because you have a different token distribution from sample to sample. So the an optimal index would be also different. I thought there was a follow-up on this reformer where there was like clustered. So instead of LSH, there were clusters to project, which is like just a better version of LSH. And there, like I'm not very sure like where HNSW could fit in, because so you would need to build it first. So that's like an engineering trade-off, like whether you should do brute force or like. So it's not very clear. So like you can, so because it's an engineering. It is an engineering problem. Like in many cases, you can't just go away go with LSH. It will be slower. Yeah, it will be less accurate. But if you like increase the size, so it might be fine. So it is hard to really predict whether it should be used there. But for the documents, I think. Like if you have lots of documents and those are like very different, and they can reside, so they don't change over time. So you can pre-build an index for them, like a graph. So that would make much more sense.
Yeah, I guess I was thinking about kind of like these contrastive learning methods where you have maybe an exponential moving average of one copy of the weights, and maybe you would cache that and build up the index of those activations, maybe some kind of pipeline like that. And then I was also
yeah, sorry. So like when you do contrastive learning, so usually the nearest neighbor search, like unless you have like a really huge data, like really huge data set, is very fast because you do it on GPU, and like you can easily search within, I don't know, 10 million vectors. Like what is the closest elements, because transformers or other networks that are run to produce those are much slower. So there I don't think like you should use them. But if you want to go like to billion scale, so like you have like a cache, and that would be meaningful.
Have you ever thought about using these vector search algorithms to search for similar activation pathways in very large neural networks?
Oh, well, yes, I did. So it's like very handy techniques to find like the problems with data sets. So like for images, for instance, if you have like if you have some like badly classified example, so you can look for similar activations in the data set. So and yeah, I used that for cleaning data sets some time ago, and yeah, but that usually works, at least for images.
Yeah, I love that application of Weaviate as a tool for doing deduplication of, say, language modeling data, and they have the merge variable, as and no Eddie knows all about that, will merge the nearby things, and I love that application of it for data deduplication. So one kind of meta question I wanted to ask is about billion scale similarity search. Just to build more intuition, could you tell us about like the application of billion scale search that inspires you and keeps you working on these problems?
Well, so there are many applications. Like I now work in Twitter. So and in Twitter there are like billions of tweets that you can show to user. Like if you are doing out of network like candidates. So yeah, there are papers. So well, there are like also like well, there are also text. So like if you want to build a really huge language model, so right now you can use a lot of text, and like also like I can mention the DeepMind paper retro. So like it depends on ANN, and like I can easily imagine billion scale there. So if you have like a billion documents, so that is like web scale. Well, even like less than web scale. I think less web scale is like 10 to 15 elements, like or more.
Okay, cool. Etienne, do you have anything to wrap it up with?
No, other than to say thank you very much. This was really insightful, and I mean it's always nice to hear the minds and the heads behind these kind of algorithms that but it's also so cool to get this additional insight of both sort of in both directions, like both in the history of what happened before. And I mean, I knew that HNSW was based on NSW, but basically that's where my history part ended. and yes, you made as you told us, it's building on so much more, and of course always research is building upon other research, and this is just very cool to see how these things come together, that we are here at this point, and also with the same in the other direction to see what's still possible, like potential integrations of something like product quantization into HNSW, and all these other kind of things. So super cool, very insightful for us. I hope it was also interesting for our listeners when we dove very deep into those topics. But I enjoyed it very much, so thank you from my side.
Yeah, thank you. That was an a nice, like an enjoyable talk to me as well. So yeah, thank you.
Thank you.
Thank you so much, Etienne and Yury, and to our listeners. Yeah, it's such a masterclass on the depth of these topics, and I'm really impressed with how much you guys have explored these vector indexing techniques, and I'm excited to be learning more about it as well. So thank you so much for watching the 8th episode of the Weaviate podcast. More to come on developing our understanding of vector indexing and these things that are available in Weaviate, which I think is such an exciting part of Weaviate that you can't overlook, is the implementation of these vector indexes that let you do very large scale similarity searches.
Yeah!